Hello, this is Dr. A. Samson Nesaraj, Professor, Department of Chemistry, School of Advanced Sciences, Kalasalingam Academy of Research and Education, Krishnankoil, Tamil Nadu, India. The focus of my research topic is nanocrystalline electrolyte materials for low temperature solid oxide fuel cell. What is a fuel cell? A fuel cell is an electrochemical device that converts chemical energy into electrical energy. Every fuel cell has two electrodes, one positive and one negative, called respectively the cathode and anode. The reaction that produces electricity take place at the electrodes. In all types of fuel cell, hydrogen is used as fuel and can be obtained from any source of hydrocarbon. The fuel cell transforms hydrogen and oxygen into electric power, emitting water as their only waste product. A simple fuel cell setup is shown in this particular slide. The chemistry of a fuel cell. Pressurized hydrogen gas enters the fuel cell on the anode side. Oxygen gas is forced through the catalyst on the cathode side. This reaction results in a transfer of electrons and ions across the electrolyte from the anode to the cathode. If an electrical load is attached to this arrangement, a complete circuit is formed and a voltage is generated from the flow of electric current. The voltage generated by a single cell is typically rather small, less than 1 volt. So many cells are connected in series to create a useful voltage. My focus of the research is SOFC. SOFC has ETS-stabilized zirconium electrolyte, which can work at 1000 degrees centigrade, produces high quality heat, no restriction on the cell configuration, power generation efficiencies could reach 60%, 85% with cogeneration. Expert research systems with up to few kilowatt can be generated. Our focus on LTOC research. Research efforts are nowadays take place to reduce the operating temperature of SOC from 1000 degrees centigrade to about 600 degrees centigrade by going in for an appropriate choice of new materials from ceramics and in evolving suitable fabrication techniques. Our research focus is one such effort to select the suitable alternate electrolyte materials based on ceramics with specific properties for low temperature solid oxide fuel cell application. Our methodology of research. Preparation of alternate electrolyte materials by wet chemical synthesis route, physical characterization of materials by X-ray diffraction, FTER, particle size measurement, SEM, and ADAX, electrical characterization of fuel cell components, recommendation of suitable alternate electrolyte components in real SOFC application. Preparation of fine SOFC particles by chemical precipitation, you can able to find out the details in this particular flow chart. Chemical precipitation, yes, in the procedure, you can find out the stages of this chemical precipitation in this particular slide. The techniques which are used for characterizing materials are depicted in this particular slide. Synthesis and characterization of doped nanocomposite ceramic oxide materials as electrolyte for SOFC. So we have carried out the research on 6 different materials for SOFC electrolyte. The details are presented in this particular presentation. Why ceria-based materials as electrolytes? The ceria-based electrolytes for SOFCs have exhibited good performance improvements that have demonstrated a breakthrough in SOFC research. New research activities on the ceria-based materials have shown superior ionic conduction with conductivity of 0.1 Siemens per centimeter below 600 centigrade. The ionic conductivity of doped ceria is nearly an order of a magnitude than that of vitreous zirconia for similar doping conditions. The TG analysis of the doped ceria precursor materials are shown in this particular slide. TGA we have carried out between 25 to 700 degrees centigrade. Evaporation of water is found at 50 to 100 degrees centigrade. Removal of organics found between 100 to 600 degrees centigrade. Phase purity found at around 650 degrees centigrade. Stable compound found out at 700 degrees centigrade. The TGA data which we obtain in our research work are presented in this particular slide. X-ray diffraction obtained on nanocomposite ceramic oxide powder, well crystalline single phase nanomaterials with cubic Fourier structure is reported in this particular slide. The standard data JSU number 810792 for ceria is compared with all the data of the materials. No extra peaks or impurity peaks correspond to any other secondary phases found in this particular X-ray diffraction patterns. The lattice parameters increase linearly with seminal content increases. The crystallographic parameters obtained on doped ceria materials are present in this particular slide. We have measured the theory density as well as crystallized size for all the materials. The unit cell parameters were calculated using DOS computer programming. The data is presented in this particular slide. FTR analysis on nano-composite ceramic oxide powders. The FTR measurements were carried out between 400 cm inverse to 4000 cm inverse. Cerium oxide peaks found at 1383 cm inverse. Carbon dioxide peaks found at around 2360 cm inverse. HOH bending found at 1598 cm inverse. OS testing found at nearly 3400 cm inverse. Most of the peaks observed in FTR spectra are similar to each powder, which shows the structural similarity in all the samples. Particle size pattern obtained on the materials are shown in this particular slide. We use small one particle size analyzer for measuring the particle size for the materials. Before the particle size measurement, we have mixed the powder in double distilled water and we have sonicated for about 10 to 15 minutes before the measurements. The particle size is found between 180 nanometer to 2241 nanometer. The higher particle size range is mainly due to the high temperature treatment of the particles. Some photographs obtained on nano-composite ceramic oxide powders are shown in this particular slide. The grain size is found to be 50 to 100 nanometer in all the materials. EDAX spectra obtained on nano-composite ceramic oxide powders are shown in this particular slide, and we have got the respective atomic weight of elements in all the materials. Impedance analysis. Complex impedance spectroscopy measurements have been carried out using a Solarton 1260 frequency response analyzer combined with Solarton 1296 electron interface. The bulk resistance RB can be determined from the intercept of the low frequency part of the R with real Z prime axis. As the temperature increases, the RB value shifts towards a lower temperature value. The bulk quantity can be obtained from the equation sigma is equal to T by RA, where T and A are the thickness and cross-section area of the pellet respectively. Activation energies correspond to the conductivity in high temperature range were determined from the linear fit of the Arrhenius curves. Activation energy of all the samples was calculated using Arrhenius relations equation, that is sigma dc of T is equal to sigma naught exponential minus EA by kBT. So this formula was used for finding the values of sigma. The impedance curves obtained on sinter circular complex of gadolinium doped ceria, yttrium doped ceria at different temperatures are found in this particular slide. So we measure the conductivity for the materials at around 300, 400, 500, 600, 600 centigrade. We have got the maximum conductivity for this material at 600 centigrade as 4.5799 into 10 to the power minus 5 Siemens per centimeter. The similar measurements were carried out for all the materials. The figures are shown in the slide. Second one, third one, fourth one, fifth one, sixth one. Activation energies calculated from Arrhenius linear fit relationship for doped nanocomposite ceramic oxide materials are shown in this particular slide. You can able to find out the activation energy for the materials 0.341 electron volt, 0.375 electron volt, 0.389 electron volt, 0.544 electron volt, 0.471 electron volt, 0.316 electron volt. They can able to find out the activation energy diagram, that is Arrhenius linear fit diagram, also in this particular slide for all the materials. Conclusions. Chemical crystallization can be effectively used for the preparation of nanocrystal materials for SOS application. TGA patterns obtained on the precursor samples reveal the methodology to get phase pure materials. The XR results were matched well with reported previous data. Particle characteristics of data and SEM analysis confirm the presence of nanometer size particles in the samples. FTA data reveal the presence of metal oxygen in all the samples. The materials tend to absorb moisture and carbon dioxide atmospheric air, which is a characteristic behavior of ceramic oxides. EDAS confirm the presence of appropriate quantities of elements in the samples. The presence of higher concentration of oxygen is due to the existence of atmospheric oxygen. The conductivity data obtained on the electric samples reveal the optimal conductivity. This is the material in which we have got maximum conductivity for our sample, that is 20 mole percent gadolinium doped ceria as well as samarium 20 mole from samarium doped ceria, which is a composite electrolyte, and the particle size is found to be 180 nanometer, crystallized size is found to be 20 nanometer, and conductivity is found to be 3.9 into 10 to the power minus 4 Siemens per centimeter at 6 degrees centigrade. We would like to acknowledge Karna University, Material Research Center, IGCAR Kalpakkam, Kalasalingam University, as well as Central Power Research Institute for promoting this research in our institute. I would like to thank the research scholar Dr. Radhika, who carried out this research work in our laboratory. Thank you one and all. Thank you very much.